Awesome. All right, well, thank you everyone for the kind opportunity to speak with you today, and for the organizers for this talk here too. And so I'd like to jump straight into phosphorus chemistry on the early Earth, specifically the prebiotic chemistry of phosphorus as we kind of are familiar with it. And to kind of raise this up in sort of the context of prebiotic chemistry. Of course, prebiotic chemistry tends to take both a top-down and a bottom-up approach. The top-down approach being the one that kind of uses modern-day biology to kind of focus on what universals seem to be present throughout life as we have it on the surface of the Earth. And one of the universals is the presence of the element phosphorus. And the element phosphorus is, of course, some of the more important parts of some molecules, such as the energy currency of life with ATP, the triphosphate being the main energy store and delivery system of modern metabolism. But phosphorus is also present in cellular structure in the form of phospholipids, where these, as Sheriff was showing, these are an important part of sort of lipid formation. Modern ones have this phosphate glycerol fatty acid groups here, but the phosphorus and the cyclic ones are obviously important in that way as well. The nucleic acids as well have the sugar phosphate backbone that kind of provides the structure and support for forming nucleic acids. And sort of the reasons for that were first outlined by Frank Westheimer in 1987, whose paper is still cited even throughout today, but has been revisited in recent times from both a more chemical perspective as well as a sort of geological perspective in some of the papers that you see down here. So the top-down approach is, of course, corresponds to the other side of that is the bottom-up approach, where phosphorus in sort of the prebiotic chemistry is sort of examined. And so the question then that we have is, how do we get here from here? So how do we form organophosphorus compounds? Through sort of geochemically plausible environments. And many of the approaches that have been taken since the 1960s have involved things such as polyphosphates, such as this triphosphate right here, cyclic trimetaphosphate or cyclic triphosphate, if you will, such as the shown right here in the structure, P309 3-, and many of them still rely on the presence of regular phosphate as being a phosphorylating agent. So phosphate in these cases is coupled to some chemistry driving the formation of organophosphorus molecules. However, the phosphorus that we tend to consider with sort of a prebiotic chemistry has a significant problem associated with it. And it's twofold. The problem is related to many other problems in prebiotic chemistry. One is that phosphorus is unreactive because the phosphorylation reaction is a dehydration reaction, which is problematic. However, phosphate is also insoluble. It is a poorly soluble element or poorly soluble mineral phase. I should note that the typical phosphate sources on the surface of the Earth include phases such as this apatite crystal that you see right here, which is a calcium phosphate, but also includes species such as iron phosphates, ferrous phosphate being known as vivianite, and rare earth phosphates such as monazite. And these are all kind of very poorly soluble and very poorly reactive towards the reactions we would anticipate for formation of organophosphates. So the solutions people have sought for sort of understanding how to form organophosphates include making these more soluble, for instance, by acidifying your oceans, having redox chemistry drive off a little bit of the divalent cations that are bound to them. Toner and Catling presented an idea last year of having abundant carbonate lakes, which would tie up your calcium, allowing for liberation of phosphate. And Ritson and others last year as well also suggested that the oxidation of reduced phosphorus could produce soluble phosphate. And then to overcome the lack of reactivity of phosphate, there are many who have sort of sought to provide more reactive phosphorus sources, such as reduced phosphorus, reduced oxidation state phosphorus by Addison Gulick in the 1950s, condensed phosphates, such as the polyphosphates, and recently the imidophosphates as well by Clementine Gibbard in the Ramakrishnan Murthy lab. I should note, and to also give credit where it's due, that if you're going to use phosphate as a source of phosphorus for phosphorylation, that is a bit akin to building your prebiotic organic inventory from carbon dioxide. In other words, carbon dioxide is a thermodynamic sink, and you have to really kind of push the chemistry to make it. Similarly with phosphate, it is the low energy form of phosphorus, and it really is kind of hard to do things. It is possible, but there are challenges associated with that. So how do we make phosphorylation by phosphate more favorable? If we draw up the chemical reaction of a simple alcohol reacting with phosphate to give you an organophosphate, releasing water. If you think about just Le Chatelier's principle, if you have more poor reactant, if you increase the concentration of reactant, say by increasing the phosphate concentration, that can drive this reaction forward. And of course, we mentioned some of those in previous ones, such as solubilizing a phosphate by acidifying or reacting, removing your calcium through some means. But the other way that it's been used as well has been to decrease the activity of water, so decrease the product concentration. And that includes things such as drying down, heating it up, but also alternative solvents such as formamide. Yoshihiro Furukawa has done recent work on that as well as so-called deeutectic solvents, which are no longer water-based, and even some that are somewhat water-based, such as the semi-aqueous solvents that are urea ammonium formate water eutectics, or mixtures, if you will, though it has been explored by Bradley Burkhardt and Jennifer Legault. So the other route to kind of making organophosphorus compounds is to let organic chemistry do the work, such as using condensing agents, reactive intermediates, and other things like that. That's to use phosphate. Now, the other alternatives is to use more energetic varieties of phosphorus beyond just the monomeric phosphate. And the one that was used primarily at the beginning was condensed phosphates. And this is based on the fact that life today uses condensed phosphate in the form of ATP to drive modern biochemistry. And however, I should note that the production of phosphates, condensed phosphates, the routes to making those are pretty few and far between. And we have a review that we kind of go through all the minerals that are present, and there are not really that many minerals that have condensed phosphates. They are certainly not widespread. And what I should also show the sort of the golden, the holy grail of phosphorylation agents, in part, has often been thought to be trimetaphosphate, which again is this ring structure, which I should note as well that Uli Muller has a paper out that shows that this trimetaphosphate can promote RNA sort of lengthening using this compound. However, as of 2020, there were no minerals that have these cyclic phosphate structures in them. There are polyphosphates that can work and substitute, and Yamagata and others propose that phosphoric acid can form P4O10, which is very similar using volcanic fumaroles. Imidophosphates are sort of a more novel idea. And again, Clementine Givard, as part of the Krishnamurthy lab, kind of explored this in a paper a couple years ago. And these compounds are excellent phosphorylating agents. They can phosphorylate nucleosides and lipids, as Sheriff just showed. And they can even make your nucleotides into nucleotide polyphosphates. They're great for sort of adding phosphate to things. Additionally, this is in equilibrium with trimetaphosphate. Using different acid-base conditions, you can have these things kind of convert from one into the other. And so, of course, the question for the imidophosphates is, what is the geochemical source? And thus far, there are no phosphorus nitrogen minerals that have been identified. The closest things are some ammonium phosphate minerals, such as the mineral struvite that Leslie Orgel looked at in the 1970s. We looked at this one as well, but did not see any production of imidophosphates, at least under sort of a simple heating style condition. So the other ways of kind of priming your system for forming reactive phosphorus is to heat the system in dry conditions. For instance, with imidophosphates, maybe adding ammonia, or to use an energetic variety of phosphorus, something that when you mix it with the conditions of the early Earth would favor production of energized phosphorus compounds. And our personal favorite are reduced oxidation state phosphorus compounds. And these include the mineral schreibersite, which is this iron nickel phosphide mineral, which is a rather common volumetrically constituent of several different types of meteorites. This is actually a big grain of schreibersite singing in an iron meteorite. And we've done research, and others have chased this compound to see what it can do for several years. In addition, there is a derived product of this that can work as well, the reduced phosphorus compounds, phosphite and hypophosphite, and other similar ones. And in these cases, one of the oxygens on phosphate's been replaced by a hydrogen, and as a result, it's prone to oxidation. So the reduced oxidation state forms that may have been present on the early Earth include such as those that we find in meteorites. And I should note as well that about the Earth, 90% of the Earth's phosphorus is actually caught up in its core. Phosphorus is an iron-loving element unless there's too much oxygen around. And in general, in space, there's usually most phosphorus is actually dissolved in metal. Recent work has also shown that you can get these minerals occurring in these lightning glasses called fulgurites. And you can get schreibersite occurring in these things as well. Now, the interesting thing is if you have schreibersite around, you add water to it, it will form phosphite. And I will show a series of NMRs, and in general, the phosphite occurs at about ppm of 4 ppm, and it also occurs as a doublet if we have a proton coupled to it. And recently, I've used the word 2020 before to identify that in 2021, there was a finding by Sergey Britkin and others that showed that there is actually a condensed polyphosphate mineral that actually has a ring structure. It is a nickel tetraphosphate, cyclic tetraphosphate that they found in some strange rocks from Israel. And we also showed 2 years ago now that if you take schreibersite and mix it in aqueous ammonia, so water that was anywhere from 14 to about 2% ammonia, you can actually make your diamidophosphates and your monoamidophosphates from that as well. Now, in addition to the phosphide minerals, the phosphite minerals are pretty possible as far as storing some amount of chemical energy. So this hydrogen and phosphorus bond has a fair bit of, when on its oxidation, is fairly energetic. In fact, if you oxidize these forms of compounds, you can form condensed phosphates fairly readily. And if you oxidize them under an aqueous ammonia solution, you can make some of the amidophosphates as well, in this case, monoamidophosphate. So some of the sources, we've already talked about meteorites. Meteorites have generate phosphite upon sort of sitting in water for a little while. Same with fulgurites. Fulgurites also have some amount of schreibersite, but they also seem to have some amount of dissolved phosphite or mineral phosphite in them as well. We have not identified the phase, but they do have some amount of phosphite. And when we've taken a look at some of the oldest rocks on the surface of the Earth, oldest sedimentary rocks, this is the Kuntaruna carbonate from 3.5 billion years ago. We separated the phosphorus species by chromatography and actually do see some amount of phosphite in these rocks. We're not sure of the source of that, but we proposed at the time that it was meteoritic. However, there is also roots to forming phosphite by coupling the oxidation of iron to phosphate reduction. So if you take iron 2 and add phosphate to it, you can actually produce phosphite. And you see the peaks corresponding to phosphite in these sample experiments. And we've seen this in old rocks as well. And then a type of rock that got a lot of love the previous session was serpentinites. And serpentinites are formed from the sort of water reactions with ultramafic rocks. And when we analyze extracts of serpentinites, we actually do see phosphite as a major component of some of these things in a paper that we have in preparation. And then finally, and perhaps most volumetrically important, is the production of phosphite in impactites. Now, meteorites are a point source of material, but in largest impacts, there is the robust formation of a lot of something called distal impact ejecta, such as spherules and glasses. And in many of these, we actually find phosphite as an important constituent. It's probably formed by a very similar process as lightning, but it is still pretty interesting that this is so abundant in these types of materials. So to summarize, prebiotic phosphorylation could occur through many routes involving condensed phosphates and heightened solubility of phosphate or energetic forms of phosphorus. Most of these routes rely on the Earth being somehow kind of different than the present day, such as the high carbon dioxide atmosphere, acidic water, or the high meteorite flux, high lightning flux, high cratering rate of the early Earth. And all these could have driven phosphorylation as being a favorable methodology. And then finally, reduced phosphorus forms, both phosphides and phosphites, would have been present and could have served as a feedstock for prebiotic phosphorylation power. So with that, I can say thanks and hand this over as well.